Imagine a small metal cylinder that weighs less than 2 kilograms, spinning at an incredible 20,000 revolutions per minute inside a sealed housing about the size of a microwave oven. At that speed, even an imperfection as thin as a human hair can throw the entire system off balance. The result? Intense vibrations, rising temperatures, and enough centrifugal force to bend solid metal. The surprising part is where you'll find it. This tiny but incredibly powerful machine sits beneath the floor of a 4-seat Tesla sedan. It's Tesla's revolutionary carbon fiber-wrapped electric motor. What makes this motor truly fascinating isn't just the breathtaking acceleration it delivers. The real mystery is something most people never think about. How can an electric motor spin at such extreme speeds without tearing itself apart? The answer lies in a feature that's almost impossible to notice from the outside: a thin layer of carbon fiber wrapped tightly around the motor's rotor. In this video, we'll answer 3 important questions. First, how does this carbon fiber layer prevent the rotor from flying apart at extremely high speeds? Second, if Tesla made the patents for this technology public, why haven't other manufacturers successfully copied it? And finally, is this motor designed only for electric cars, or is it part of a much bigger plan that extends far beyond the automotive industry? Let's find out. When speed becomes the biggest challenge, to understand why Tesla went to the trouble of wrapping its rotor with carbon fiber, we first need to understand what a rotor actually does and the enormous stress it experiences. Every electric motor has 2 main parts. The first is the stator, the stationary outer section that generates a rotating magnetic field. The second is the rotor, the component that spins inside the stator. As it rotates, it converts electromagnetic energy into mechanical motion, ultimately turning the vehicle's wheels. For well over a century, electric motors have relied on rotors made from silicon steel combined with copper windings. This design has proven to be durable, affordable, and relatively easy to manufacture, making it the standard choice across countless industries. However, every material has its limits, and those limits become increasingly obvious as rotational speed rises. One of the biggest challenges is centrifugal force. It doesn't increase in a simple, straight-line relationship with speed. Instead, it grows dramatically as the rotor spins faster. That means doubling the motor's speed doesn't simply double the stress, it increases it several times over. According to the available data, once a silicon steel rotor reaches around 18,000 revolutions per minute, the internal stress approaches the material's strength limit of roughly 350 megapascals. Beyond that point, the metal doesn't instantly fail. Instead, it begins to deform on a microscopic level. These tiny distortions might seem insignificant, but they quickly create vibrations. Those vibrations produce friction. Friction creates heat, and the extra heat reduces the motor's efficiency, exactly when maximum performance is needed. A simple example makes this easier to imagine. Picture a metal wheel spinning slowly. It stays balanced, smooth, and stable. Now imagine spinning that same wheel dozens of times faster. If even one tiny section expands slightly more than the rest, the entire wheel begins to wobble. At low speeds, that wobble may not matter much, but at extremely high speeds, it can become powerful enough to damage or even destroy the entire system. That's essentially what happens inside a traditional silicon steel rotor when it's pushed beyond its safe operating range. The real challenge isn't just reaching high speeds for a few seconds. The rotor must maintain its exact shape while repeatedly heating up, cooling down, and operating under heavy loads throughout the entire life of the vehicle. For decades, this limitation has acted as an invisible barrier, preventing electric motors from becoming both faster and more powerful. Tesla decided it was time to overcome that barrier. A thin layer with incredible strength. On the surface, Tesla's solution sounds surprisingly straightforward. Wrap the rotor in carbon fiber. Simple in theory, but extremely difficult to execute. We'll discuss why later. First, let's look at the numbers. The carbon fiber used by Tesla has a tensile strength of more than 2,400 megapascals. That's several times stronger than silicon steel, which can withstand only about 350 megapascals before reaching its limit. According to the original source, this carbon fiber is even more than 3 times stronger than Inconel 718, a high-performance superalloy widely used in aircraft jet engines because of its exceptional strength under extreme conditions. In other words, Tesla surrounds the rotor of its electric motor with a material that's stronger than many of the alloys trusted by the aerospace industry. What's even more impressive is how little of it is needed. The carbon fiber layer is only about 2.5 millimeters thick, roughly thinner than a bank card folded a few times. Despite its thin profile, this layer performs an incredibly important job. As the carbon fiber is wound around the rotor under precisely controlled tension, it creates a constant inward compressive force. You can think of it like an incredibly strong belt wrapped tightly around the rotor, holding every internal component firmly in place. This continuous clamping force prevents the metal beneath it from expanding outward as rotational speed increases. Instead of allowing the rotor to deform under enormous centrifugal forces, the carbon fiber keeps everything compressed, balanced, and structurally stable, even at speeds that would normally push conventional rotor materials beyond their limits. This constant pressure keeps the rotor from expanding or coming apart as its speed increases. As a result, it can safely spin at nearly 22,000 revolutions per minute, well beyond the speed where traditional silicon steel rotors begin to struggle. It's important to understand that the carbon fiber layer isn't simply a protective cover, like armor shielding the rotor from outside damage. Instead, it plays an active structural role. It continuously supports the rotor, keeping its shape perfectly stable even as temperatures rise and rotational speeds change during operation. Because the rotor maintains its shape so precisely, several important benefits follow. Vibrations are greatly reduced, energy losses caused by friction and eddy currents become smaller, and less heat is generated while the motor is running. This allows the motor to maintain high efficiency, even during long periods of high-speed operation. Perhaps the biggest advantage, however, is something that happens inside the motor itself: the ability to reduce the distance between the rotor and the stator. The tiny gap that makes a huge difference. Inside every electric motor, there's a very small space between the spinning rotor and the stationary stator. Engineers call this the air gap. Although it's incredibly small, this gap is where the magnetic field transfers energy from the stator to the rotor, converting electrical energy into mechanical motion. In general, the smaller this air gap is, the more efficient the motor becomes. A shorter distance allows the magnetic field to transfer energy more effectively, reducing wasted energy. The problem is that shrinking this gap has always been risky. If the rotor vibrates or shifts even slightly at high speed, it can make contact with the stator. Since both components are spinning and operating under extreme forces, even a tiny collision can cause serious damage. For decades, motor designers had to compromise. They could either leave a larger gap for safety or reduce it to improve efficiency, but not both. Tesla's carbon fiber-wrapped rotor changes that equation. Because the carbon fiber keeps the rotor exceptionally stable, engineers can safely reduce the gap between the rotor and stator. According to the source material, this gap can be reduced by roughly 50% compared to a conventional motor design. That may not sound dramatic at first, but the impact can be significant. The same source estimates that a smaller air gap can reduce peak electrical current by around 15 to 20%, while increasing torque by approximately 25 to 30%. It's worth noting that these figures are estimates from the source, not guaranteed performance numbers for every situation. Actual results vary depending on operating temperature, driving conditions, motor load, and many other factors. Even so, they highlight the enormous potential of this engineering improvement. A motor that requires less electrical current to produce the same amount of power naturally generates less heat. Less heat means the cooling system doesn't have to work as hard. Since the cooling system also consumes electricity from the battery, reducing its workload saves energy. That saved energy can then be used to extend the vehicle's driving range. In other words, a microscopic improvement inside the motor, reducing the air gap by just a few dozen micrometers, can create benefits that improve the performance of the entire vehicle. By now, it's clear why the carbon fiber layer is such an important innovation. But an even more interesting question remains. If Tesla has made all of the patents for this technology publicly available, why haven't other manufacturers been able to build the same kind of rotor at scale? The patents are public, so what's the real secret? This is the part of the story that surprises many people. Tesla has openly published the patents covering its carbon fiber-wrapped rotor technology. In theory, any engineer, automaker, or startup can download the patent documents, study every design detail, and attempt to build the same system. At first glance, this appears to be an unusually open approach, almost as if Tesla is encouraging the entire electric vehicle industry to adopt the technology. But having the blueprints isn't the same as mastering the process. Think about a piece of music. Every note, rhythm, and instruction can be written perfectly on sheet music for anyone to read. Yet that doesn't mean every orchestra can perform it with the same precision, emotion, or technical excellence. The sheet music provides the instructions, but the performance depends on years of practice, highly skilled musicians, perfectly tuned instruments, and experience that simply can't be captured on paper. Tesla's manufacturing process works much the same way. Wrapping carbon fiber around a high-speed rotor isn't an ordinary production step. It requires highly specialized robotic systems capable of placing every strand of carbon fiber with micrometer-level precision, an accuracy measured in thousandths of a millimeter. Throughout the entire winding process, the system must constantly monitor and adjust the tension applied to each strand of carbon fiber. According to the source material, that tension must remain within a narrow range of approximately 100 to 200 newtons. Maintaining that level of precision requires extremely fast feedback systems and continuous real-time adjustments. Even a slight variation in tension could affect how the carbon fiber compresses the rotor, reducing both performance and long-term reliability. In other words, while Tesla's patents explain what needs to be done, successfully manufacturing the rotor depends on knowing how to do it consistently and repeatedly at production scale. That's the part that can't simply be copied from a patent. At the same time, the system must monitor the surrounding temperature, adjust the winding angle to match the rotor's design, control the speed of the winding head, and finally perform a laser inspection to detect even the smallest defect before the rotor moves to the assembly line. What makes this process so difficult to copy isn't just the complexity of each step. It's the fact that every variable has to be monitored and adjusted continuously at the same time. The carbon fiber temperature changes, the winding speed changes, and the position of the machine head changes throughout production. A system that performs perfectly at the start may not maintain the same precision by the end of the process. And this is the point many people overlook. Every rotor that fails testing isn't simply discarded. It's treated as valuable data. Each failure is recorded, studied, and used to improve control software, fine-tune the equipment, and strengthen quality inspection methods. After years of collecting this information, Tesla has built more than just an advanced production line. It has created a massive database showing exactly how rotors fail, and more importantly, how to prevent those failures. That knowledge isn't written in any patent. So the real challenge for competitors isn't understanding the design. It's matching Tesla's specialized machinery, years of testing data, real-world experience, production software refined over countless manufacturing cycles, reliable material supply chain, and the ability to maintain consistent quality while producing at scale. The patents reveal the destination, but they don't provide the path needed to get there. A competitive market without a clear winner. So where does this leave Tesla compared to the rest of the electric vehicle industry? The answer isn't as simple as saying Tesla is far ahead of everyone else. BYD is a strong competitor, but it follows a very different strategy. Rather than pushing a single motor to its limits, BYD focuses on controlling nearly its entire supply chain. The company manufactures many of its key components itself, including batteries, semiconductor chips, and electric motors. This gives BYD a significant cost advantage, which it is using to expand rapidly across Europe, Latin America, and Southeast Asia. It's also worth noting that BYD has outsold Tesla in electric vehicle sales during certain periods and under specific measurement methods. However, those rankings change over time and vary by region, so they shouldn't be seen as permanent. Lucid Motors tells a different story. From a technical standpoint, Lucid has developed impressive technology. Some versions of the Lucid Air have achieved an officially published driving range of more than 500 miles under certain conditions, outperforming many rivals. But advanced technology alone doesn't guarantee market success. Lucid's production volume and sales remain much smaller than Tesla's, making it difficult to compete on the same manufacturing scale. Ford and General Motors face another challenge entirely. Both companies have invested billions of dollars in electrification, with the source estimating nearly $50 billion in total investment. However, unlike companies focused only on electric vehicles, Ford and GM still depend heavily on their traditional gasoline-powered business, which continues to generate most of their revenue. Their reliance on outside suppliers for key components like batteries and motors also slows their transition compared to companies that control more of their own supply chain. Toyota has taken an almost opposite approach. Instead of competing for the highest motor speeds or the fastest acceleration, Toyota is placing its long-term focus on solid-state battery technology, aiming for greater safety, stability, and durability. Its strategy emphasizes long-term reliability over headline-grabbing performance. Overall, Tesla's biggest strength lies in its ability to combine motors, batteries, software, charging infrastructure, and large-scale manufacturing into one tightly integrated system. So far, no competitor has fully matched that level of integration, but that doesn't mean Tesla's lead is guaranteed forever. No technology company, no matter how far ahead it is today, can assume it will always stay on top. When a car motor reaches beyond the road, this is where the story takes an unexpected turn. During the unveiling of Tesla's Plaid motor, most people focused on its incredible acceleration. But one important detail received far less attention. Its outstanding power-to-weight ratio, excellent thermal stability, and ability to operate continuously at extremely high rotational speeds make this motor suitable for applications that extend well beyond a conventional passenger car. The electric aviation industry, especially the fast-growing field of electric vertical takeoff and landing aircraft, or eVTOLs, has faced a challenge very similar to the one Tesla solved with its carbon fiber-wrapped rotor. A motor designed for an aircraft must meet several demanding requirements at once. It has to be lightweight so it doesn't reduce payload, powerful enough to generate lift, capable of handling repeated high loads without losing performance, efficient at managing heat, and above all, highly reliable. Unlike a car, where a breakdown is inconvenient, a motor failure in the air could have far more serious consequences. With its lightweight design, optimized rotor, stable high-speed operation, and excellent power-to-weight ratio, Tesla's motor could theoretically attract interest from companies developing electric aircraft. However, it's important to be clear that Tesla has never officially announced plans to use its Plaid motor in eVTOL aircraft. For now, it's an industry possibility, not a confirmed project. Even if that were to happen, a motor built for a car would still have to meet strict aviation requirements, including flight certification, safety regulations, emergency backup systems, and durability standards far beyond those required for road vehicles. Beyond aviation, the same advantages, high power output in a compact package, could also make this technology valuable for industrial robots and automated machinery, where space is limited, but high performance and precision are essential. What do car buyers really care about? After exploring all this impressive engineering, one important question remains. Do most buyers actually care about these technical achievements? For most people, the answer is probably no. Few customers choose a car based only on its 0 to 100 km per hour acceleration time. Instead, they usually focus on practical concerns like annual insurance costs, repair expenses, battery life after years of use, how much driving range is lost in cold weather, charging time, the availability of charging stations, resale value, software updates, and how comfortable they feel relying on a highly connected digital vehicle. According to independent testing referenced in the source, an electric vehicle's real-world driving range can drop by roughly 30 to 40% in temperatures near 0 degrees Fahrenheit, or extremely cold conditions. That figure isn't universal though. It varies depending on the vehicle, battery type, driving style, and testing conditions, so it shouldn't be treated as a fixed value for every EV. Insurance is another consideration. In some markets and for certain drivers, Tesla vehicles can cost noticeably more to insure than comparable gasoline-powered cars. The exact difference depends on many factors, but it raises an important question. Is having one of the world's most advanced electric motors enough to convince everyday buyers if ownership costs and long-term reliability remain concerns? Tesla is becoming more than a car company. To understand Tesla's position today, it's important to look beyond its vehicles. In recent years, the company has quietly expanded into a much broader energy ecosystem. Its Megapack systems provide large-scale battery storage for utilities and businesses. Its AutoBidder software automatically manages and trades stored electricity in wholesale energy markets. The supercharger network supports Tesla owners with a dedicated charging infrastructure, while its gigafactories bring together vehicle production, battery manufacturing, and energy products under one roof. According to information referenced in the source and dated June 2026, Tesla planned to deploy about 25 gigawatt-hours of Megapack storage in the United Kingdom and Italy, with contracts estimated at around $5 billion. This information reflects that specific time period and shouldn't be viewed as continuously updated data. The bigger takeaway is that Tesla's greatest advantage may not be any single product, not even its carbon fiber-wrapped motor. Its real strength comes from how every part of its ecosystem works together. The vehicle communicates with intelligent management software. That software optimizes battery usage. The navigation system directs drivers to the nearest available supercharger. Those charging stations connect to large-scale energy storage systems, while the entire network is supported by automated energy management software. Rather than building individual products, Tesla is building a connected ecosystem in which every component strengthens the others. This entire ecosystem is far more difficult to copy than any single motor, no matter how advanced that motor may be. Lessons from technologies that once seemed unbeatable. The history of technology has shown time and again that having the better product doesn't always guarantee long-term success. Betamax was once considered a superior video format, yet it lost the market battle. BlackBerry dominated the business phone industry with its famous physical keyboard, but couldn't keep up with the shift to touchscreen smartphones. Nokia once ruled the global mobile phone market, only to lose that position much faster than anyone expected. These examples don't take away from the genuine engineering achievement behind Tesla's carbon fiber-wrapped rotor. Its thermal stability, the exceptional strength of carbon fiber, and the manufacturing advantage created by Tesla's AI-controlled winding process all represent real technical progress. But the electric vehicle industry is still evolving, and many other factors could reshape the competition much faster than advances in motor technology alone. Battery prices continue to fall across the industry. Solid-state batteries could become the next major breakthrough. Government incentives for electric vehicles can change with a single election. Tariffs, supply chain disruptions, and global market conditions can quickly shift the competitive landscape. And in the end, consumer trust remains the deciding factor. Even the long-term durability of a rotor spinning at nearly 22,000 revolutions per minute is still an open question. Running a motor at such high speeds in a consumer vehicle that's driven every day for years may involve a balance between peak performance and long-term durability. This doesn't mean high rotational speed will definitely shorten motor life. It's simply an engineering question that can only be answered after many years of real-world experience and testing. The story is still being written. Looking back at everything we've covered, it's clear that Tesla's carbon fiber-wrapped rotor is an impressive engineering breakthrough, because it solves a challenge that has limited high-speed electric motors for decades. But its greatest value isn't just helping the Model S Plaid accelerate a fraction of a second faster. Its real importance lies in increasing power density within a compact design, improving energy efficiency, reducing heat losses, opening possibilities in industries like electric aviation and industrial robotics, and strengthening the larger technology and energy ecosystem Tesla has spent years creating. At the same time, one important reality remains. The future of the electric vehicle industry won't be decided by motor technology alone, no matter how advanced it becomes. Battery innovation, manufacturing costs, long-term reliability, charging infrastructure, government policies, after-sales support, and most importantly, consumer trust will all play equally important roles. So here's the question I'd like to leave you with. In the long run, which strategy do you think will come out ahead? Tesla's approach of combining high-performance motors with a fully integrated ecosystem, or Toyota's more cautious strategy focused on the long-term safety and durability of solid-state battery technology? If you already own an electric vehicle, or you're thinking about switching from a gasoline-powered car, I'd love to hear your thoughts in the comments. The opinions of people who actually drive these vehicles, or are preparing to buy one, are often more valuable than any expert analysis. If you found this video informative and learned something that typical news coverage often overlooks, consider leaving a like. It helps the channel reach more people who want thoughtful, in-depth explanations instead of just eye-catching headlines. And don't forget to subscribe.